Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 5B. My name is Alesha Mulla, and I will be your moderator for this session. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, ICICT 2026, in London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in London, and the virtual event is being held on Zoom from 25th to 27th February. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we will be having 6 presentations. Each presenter will be given 12 minutes for the presentation and 3 minutes for question and answer. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants. Please stay connected with us till the closing remarks. If you have any query or update, you can write it to me in the chat box. Before we start the session, I would like to introduce you all to the chair for this session. Dr. Firas Shaukat Hamid is an assistant professor at Northern Technical University, Iraq, specializing in communications engineering and computer systems. He holds a PhD with expertise in aviation electronics or avionics and has conducted research in blended learning, computer networks, and user experience enhancement. Dr. Hamid is actively engaged in teaching and research, contributing to the advancement of technology-driven education and communication systems. I would like to request Dr. Hamid to say a few words.
Hello, everyone. You asked start for my presented. I prepared about start this session. Good afternoon, distinguished colleagues, ladies and gentlemen. Welcome to session 5 of the ICICT 2026 of the conference taking place here in virtual room B. My name is Dr. Firas Shaukat Hamid, and I will be serving as the session chair for this session together with my colleague, Dr. Bitan Misra. At the outset, I would like to express our sincere appreciation to the conference organizers, the technical program committee, and all supporting staff for their excellent efforts in making this event possible. This session features a diverse set of high-quality research contributions covering medical imaging, EEG-based speech analysis, artificial intelligence, data augmentation techniques, GIS-based socioeconomic studies, and medical diagnosis technologies. We have 6 papers scheduled for this session. Each presenter is allocated 12 minutes per presentation, followed by 3 minutes for questions and discussion. I kindly ask all speakers to adhere strictly to the allocated time to ensure a smooth and productive session for everyone. Without further delay, let us begin with the first presentation entitled GaussNet for Few-Shot Medical Image Classification in Low Resource Setting, presented by researcher Kunal Kumar Pant. You now have the floor.
Kunal, you may start your presentation. Thank you.
Sure. Just let me know if you're able to see my screen.
Yeah,
are you able to see my screen?
Yeah, we can see it.
All right. So thank you. Hello and a very good evening to the channel, panel, moderators, and participants. Thank you very much for having me. My name is Kunal Kumar Pant, and I'll be presenting our work on ChaosNet for few-shot medical image classification in low-resource settings. I'd like to start off by saying that this is my first presentation of any research paper in general, so I apologize if I mess up anywhere beforehand. Um, so our work explores whether a brain-inspired neurocures learning model can compete with the classical machine learning approaches when the medical data is extremely limited. The central question we want to ponder upon is that when data is scarce and imbalanced, do we have alternative architectures which perform competitively to the existing models we have currently? Um, so healthcare AI faces a fundamental contradiction, as I said. We need AI most in critical conditions, but those are exactly the cases where the data is limited and imbalanced. So it creates sort of a paradox where models typically assume large annotated data sets, high computational resources, and a balanced training data. But specifically in medical imaging and healthcare in general, the data is pretty expensive. The rare diseases are underrepresented and class imbalance is pretty common. So our goal was to again evaluate whether this new novel neurocures learning could provide a competitive alternative in low sample regimes. Um, Neurocures learning, or NL, is inspired by nonlinear chaotic firing patterns observed in biological neurons. Instead of layering through or learning through backpropagation, neurocures learning applies nonlinear chaotic transformations and extracts chaos-based features. There are two major architectures where we can employ neurochaos learning. They are namely ChaosNet and ChaosFX plus ML. ChaosFX utilizes chaos features, which are then of use to a different type of ML or DL classifier. However, in this work, we primarily focus on applying ChaosNet. The motivation is to test whether these chaos-based representations can generalize well under this type of data scarcity. ChaosNet is built using 1D or one-dimensional chaotic maps known as the generalized Leurot series maps. So essentially, if we sort of imagine the brain, each neuron is imbibed by a chaotic map, which is the GLS neuron map. For each particular class of the dataset, the model comprises a mean representation vector, which consists of the mean firing rate, the mean energy, the mean entropy and the mean firing time. So for each class K, we have all of these parameters, and it uses then the cosine similarity of the test data instances with the mean representation vectors to find out the results. In the other type of neurochaos learning we talked about in the previous slide, chaos FX, instead of using cosine similarity, we can use some other types of ML or DL classifiers. All of this work has been done since 2019, and it has been employed on various different researches, general ML data sets, my own work on forest fire classification, and also more architectures are being found as I present now. The data sets, we've primarily used three data sets. All of these are taken from the MedMNIST collection of 2D and 3D image data sets for various healthcare related purposes. These all are specifically 2D data sets. The first dataset, Blood MNIST, is a dataset of individual normal cells, key for diagnosing hematological disorders, which make it possible to detect blood abnormalities such as leukemia or anemia in an efficient manner. The datasets comprises of eight classes, which are further divided into training, test, and validation splits. OCTEMNIS, the second dataset, consists of over 1 lakh retinal optical coherence tomography images. It has 4 diagnosis classes, and it can be used to detect diseases such as diabetic macular edema and vision loss by producing high cross-sectional images of the retina. Um, this particular dataset, the OCTEMNIS dataset, is dominated by low contrast and sparse pixel intensities. Then the third dataset, the breast MNIST dataset, is consisting of 780 ultrasound images converted to binary classification. So essentially, we treat the normal and benign cells as one class and the malignant as the other. And it also has a 7:1:2 split for the training, validation, and test data sets in particular. We have chosen, I have particularly chosen these three data sets so that we have across the board different type of data sets to test and train upon and essentially give out a comparative analysis of what we're trying to do here. We have compared our ChaosNet model against some ML baseline models such as SVM, KNN, random forest, decision trees, and logistic regression. The same type of comparative analysis have been performed on several different type of domains as well. And thus we have inspired to take the same type of thing. The hyperparameter tuning for the ML datasets was done via a 20% stratified split. And for OCTEMNIS specifically, we took a 20,000 subsample to reduce the computational resources and the runtime because the original dataset, as I talked about, consisted of over a lakh of images. This is the core contribution of the study. We have evaluated under a low sample training regime. This means we are training with only 1 to 10 samples per class while performing 100 random trials per setting. In each trial, a new random subset of training samples is selected. The model is trained and evaluated, and then the performance is averaged across the trials. This specifically ensures that the results reflect expected generalization rather than what we call lucky sampling. And essentially, the setup kind of simulates real-world clinical scenarios where labeled data is scarce. We also use macro F1 as the performance metric rather than accuracy because it performs well for imbalanced classes. Um, as you can view on the slide, these are the results we were able to achieve. I'll go one by one. For blood MNIST, ChaosNet achieved around zero point 0.5 macro F1 score. It consistently outperformed the baseline ML models across the sample sizes. So as you can see in the graph, as we increase the number of samples per class, the models start to perform and eventually sort of reach a saturation point. But across the board, for this particular dataset, ChaosNet outperformed all of the models. Moving on to OctMNIST, here ChaosNet scored 0.23 F1 score and SVM performed the best. Although when specifically looking at it, both of the models, they don't have much of a difference. But that is because of the low sample training regime and because the models are specifically getting a very less amount of training samples to train upon. And also because OctMNIST, after flattening and compression, initially it consisted of quite sparse images where the pixels were mostly dominated by black ones. And even after compression, it is very difficult to extract the important features from the images, thus explaining the low scores for all of the models. Then the third data set, which is the breast MNIST data set. Here, ChaosNet achieved around 0.54 macro F1 score. It was very competitive with logistic regression and random forest here, but a logistic regression performed the best with a 0.558 macro F1 score here. Overall, we can see here that ChaosNet gives us a balanced performance with different type of data sets while offering a competitive edge to the existing architectures also. However, in certain instances like the OctMNIST data set, where the images were initially too sparse and too difficult to operate upon, all of the models, and specifically ChaosNet, was not able to perform that well. I'd like to give the conclusions. As I said, ChaosNet performs competitively in few-shot medical imaging. It excels in structured datasets like blood MNIST. It struggles in low contrast fast datasets like OctMNIST. And this essentially suggests that chaotic feature extraction works well when discriminative patterns are retained. The results demonstrate that NeuroChaos learning is kind of a viable alternative in low resource settings. Some scopes for future work include integrating deep learning feature extractors, for example, convolutional neural networks with NeuroChaos learning, or any other type of robust ML classifiers. So, like we talked about Chaos FX plus ML, where we can use chaotic features and add them to a sort of an ML or DL classifier, or we can go the other way around, where we can do the feature extraction using some sort of ML or DL model and only use cosine similarity as the classification part. Then we can use optimized chaos-based features. We can further improve the hyperparameter tuning, and we can also, employ further newly improved architectures like the RHNL architecture or the random heterogeneous neurochaos learning architecture. The Essentially the crux here is that the particular neuron as a single unit, we can use different sort of functions inside it. Currently, ChaosNet employs the generalized neuron series, but you can use a logistic network neuron like RHNL uses, or you can further use different things, and there is further research going there as well. We can do a multi-model data integration, like many other domains are doing, where we employ different types of input data to provide a more comprehensive diagnostic framework. And finally, we can work on interpretability and clinical impact. Essentially, we can make sure that we are able to understand what the chaotic features actually represent and what they actually mean, sort of going into the explainable AI part of it, using SHAP analysis and other things to essentially understand and prune out what details the features are giving us and what we can make of it. These are some of the references I've noted down, and
Mhm.
thank you very much for allowing me to present.
Thank you for your presentation. We will now open the floor for questions. Okay, I have questions about. My question is, can your model generalize to real world or large scale data sets?
To answer a wonderful question. So I have done one more work on forest fire classification, as I said. That work essentially incorporated ChaosNet and several different models like RHNL into forest fire classification across Algeria, Portugal, and Canada. It is currently submitted and under review as a journal paper. And there we have done high sample training regime, like you said, over large scale data, and also low sample training regime. And ChaosNet and many type of NeuroChaos learning models have actually outperformed many existing architectures at that area.
Thank you once again for your contribution.
Thank you very much.
Thank you,
Our
Kanika.
next, yeah, I'm
Uh,
sorry.
Alright. Okay. Our next presentation will be by Harpreet Singh, who will be presenting characterizing neural mechanisms of speech modalities with EEG functional connectivity. Harpreet, you may start your presentation.
Yeah, thank you, thank you. Good morning, good afternoon to everyone. Let me share my screen first. One second. Are you guys able to see my screen?
Yeah, it's visible.
Okay. Great. Okay, so my name is Harpreet Singh. I'm a researcher and a PhD student at University of Lethbridge. Uh, in Lethbridge, it's also called CCBN, Canadian Center of Behavioral Neuroscience. So today I'm gonna represent my last year research work on on different speech modalities, uh, like uh, to characterize them and only using EEG functionality and there are some other functional connectivity tools which I have used to do it. So let's start. So in this presentation, I will be moving you guys forward with this, from where I started, my motivation, the methodology which I used, and for the analysis, connectivity analysis, what things we have used, what algorithm we have used, and what deep learning component I have used here, and the key outcomes which I got. So the main is from where I started is there is a gold standard paper on Nature's, which is called Thinking Out Loud, and I used this paper, and because this they have a publicly available data set. And why I use this, because this data set is having inner speech data involved with pronounced and visual. So they are dealing with three modalities: inner, visual, and pronounced. So this is what I choose this paper to start framing my problem and everything. So what I got here is questions what arises here is to what extent can EEG based BCIs can reliably decode inner speech. So main focus is on inner speech only. Second, so if the signal processing and machine learning strategies, whether they can improve inner speech decoding in BCA system or not, and how reliably it can be done. So these are the questions which arises, and I started my research on it. So let's dive in. We did like functional connectivity and directed connectivity across four EEG frequency bands. So there are five basically: delta, uh, theta, alpha, beta, and gamma. So we only choose from theta to gamma bands only because we are dealing with inner speech and muscle movement, and all these things. So here, what we got, so we have distinguished like inner and like pronounced speech both. So using like spatial and temporal mechanisms, we checked everything. So we can clearly distinguish both of them right now. And third, we like second, we have also incorporated a GAN-based model, which helped us decoding the mental commands for using like from EEG. And third, for the with the GAN model, we have also used CNN feature extractor, which actually gives us the uh, like EEG data, EEG noise, latent noise, and that we basically use to train the GAN model. And so both of these things helped us get spatial and temporal EEG structure and a generative model, which improved our class separability. We can easily separate our classes. So our classes basically up, down, left, right. These are just simple classes which we took to create the classifier. And yeah, so let's move to the next. So the data set which we got is it has been taken out from the Biosemi Active 2 system. It's a 128 channel and 8 EXG channels. EXG contains like both EOG and EMG. And so the data acquisition rate is like 24 and sampling is 1K. Um, it has been recorded on 10 participants, and in which six are male and four are female. And I think one guy is a left-handed guy. So yeah, so it's a mixed data set. So are you seeing this on the screen? In this there is a fixed queue and fixed session in which there is some levels in the it's a complete session of 4.5 seconds in which we uh, let the user see the screen, and on which we have start point, there is some resting period, and then we let them see the queue events, and then again action interval, relaxation time, and then rest interval. So these are the part of the session which are performed in the data set, so that uh, we can get accurate data in different speech modalities like pronounce. Well, first is inner, then pronounce, and then visual. So okay, so here yeah, so this is the actual schema of the data set which we used here. So next, what we got here is so these are the spectral patterns. These are basically PhDs created from the difference of like di difference of difference between the power spectral density of different bands. So what we got here in these so in the first row, if we see, it's inner versus pronouns. So our main motive here is to check whether inner speech, the silent voices inside us, uh, which contains the feeling of moving something up, down, left, right, and pronounce when we are pronouncing it, whether the EG signals match somewhere in the time or not. So yeah, so we got something here. If you see the first row, we see the signals matching uh, with each other. Uh, Most prominent bands are basically which we want is like alpha and beta, and basically mostly alpha. Beta is again related to the muscles because we need to remove the muscle artifacts in the pre-processing stage. So yeah, so of course, so here we got that, and like we see in the second row, the visualized and versus pronounced. We see like there is most activities happening in the occipital area of the brain, and of course, like in the pronounce when pronounce is happening, there are some other areas also activating in which we have premotor, motor, and parietal region alongside with the occipital area. Third is the so here what we got is again when we are comparing inner versus pronounce. So visualize conditions when we are seeing something. So brain is actually working in the complex situation. It's again occipital area is very easily seen in the graph. So, so the main thing why we did it, why PSDs are being done here, and so it's just to get the most prominent EEG channels, or or we can say candidate features for the BCIs. So yeah, so
Please note that you have 1 minute remaining.
okay, got it. So. So this is the functional connectivity coherence. Mm, Again, it is basically like EEG synchronization happening between several EEG channels. So we did that here, and third is like directed connectivity. Like once, when if there is something happening in one side of the brain, and how that can be affecting the some event happened in on the other side of the brain. We calculated those things here, and we got that how like sensory area of the brain is acting to the motor area, and how planning is happening. So we got some details into that as well. So this is the GAN model which we introduced here. You can see we have introduced CNN. We segregated the latent noise. We fed that to the generator model. We have a discriminator, and we got some of the real images in the probability space, which can use to classify different classes here. So, so what we got here, we got probability spaced analysis, and so analysis for
Your time is up. Excuse me, your time is up. Okay, you can continue speedily, please,
yeah, it's
about the
just
conclusion and the results.
okay, got it. So it's just two slides. So here we got we can see in probability space analysis, we can see that how a trained can translate EEG derived latent noise into class specific arrows directly. And second, we have successfully got uh, like uh, uh, data where EEG derived latent noise is classified and can be used in the BCI. So, so we got some good results here with this. So our classes is separated. BCIs can be improved here, and we got the classifier which can classify inner speech data. So the limitations which we got here is again So the data set is very small. There is an increase of overfitting. And second, cross validation. We need since like data set is very small, so we cannot properly cross validate with the other data sets. So we are trying to get more data, more subjects, so that we can train our model perfectly and in a more generalized way. Third is the last. So conclusion is again the same thing. We can broad like uh, we can see that inner speech and pronounced speech both can be correlated and can be so they are they are like we can okay. So yeah, so combining functional coherence and directed G-ranger connectivity can give us better neural fingerprints. We can see what channels, EEG channels can be used for the BCI and which can be discarded. So higher dimensionality of the channels of like EEG machines can be moved down to like 10, 20 channels only. So and yeah, so and GAN-based mapping offers a better framework to access separability, and it can be used as a non-invasive SSI outputs. So yeah, so
Okay, Mr. Arbrit, thank you
thank
for your presentation. We will now open the floor for questions because you took about 15 minutes, not 12 minutes.
sorry.
Any questions? Did your analysis reveal modality-specific network reconfigurations rather than localized critical effects?
So in this
About
research,
the network level, insights.
yeah, so like we have a biosemi 128 anatomical grouping in which we have already grouped our channels like frontal, prefrontal, parietal, occipital, or motor cortex area, and left, right occipital. So like and of course like L Broca's area and Vanix area. So we have localized as you see here, we have localized channels that which brain area is actually talking to which another brain area and what brain areas are affecting each other. So yes, we have got that data accurately.
Okay, thank you once again for your contribution.
Thank you very much.
Our next
Thank you.
presentation, okay, if you
Uh,
wanted to present this.
yeah, thank you. Our next presenter for today is Aniruddha Joshi, who will be presenting data augmentation for printed circuit board defect detection, a performance-based analysis of GAN architectures. Aniruddha, you may begin.
Oh, am I audible? Yes, thank you.
Yeah, you are.
Yes. Yes, so thank you and greetings everyone. I'm Aniruddha Joshi from a third year BTech student from PES University in India, and I will be presenting a research titled Data Augmentation for PCB Defect Detection using GAN Architectures. So the authors of this paper are Hariharan, myself Aniruddha Joshi, Dr. Richa Sharma, Professor Nivedita, and Professor Deepa. This will be my agenda for today. Yes. So our problem statement was originally given by the Space Applications Center, which is a body of the Indian Space Research Organization. So automated uh, uh, detect defection, defect detection in electronic components, specifically PCBs, is important since these are pretty expensive to manufacture. But defects are also rare, so the data set is not uh, available for this. It's very small, and training CNN architectures or any ML model for that matter would require a large amount of data. And traditional augmentation techniques aren't very effective for this. So some of the key research gaps that we identified were that of course, there's a scarcity in defected PCB data, and traditional augmentation techniques like rotation, flipping, and scaling do not really create new defect patterns. It's essentially the same data over and over again, and this could highly lead to overfitting in the our ML models. We also found that there is a limited comparative analysis of GANs, and even ensemble approaches for this were unexplored. So our objective with this project was to generate synthetic PCB defect images and to compare the performance of DCGAN, CGAN, and CWGAN GP for data augmentation, followed by evaluating their quality using FID and TSTR metrics, and also evaluating the performance of a weighted ensemble of these. So our dataset is a publicly available dataset from Kaggle, which has 6 classes: missing hole, mouse bite, open circuit, short, spur, and spurious copper. As we can see, the dataset is quite small but balanced. Coming to a methodology, our pre-processing for all the 3 models was same. So we start off by resizing the images to a standard 128 by 128 pixel size, then convert them to a 3-channel PyTorch tensor and normalizing them. Then we divide them into batch sizes of 64 and use them to train our 3 models. Then we create a weighted ensemble of these and evaluate the performance. Coming to our GAN architectures, for deep convolution GAN, we perform adversarial training of the generator and the discriminator using a BCE loss function. Conditional GAN is essentially the same loss as DC GAN, but with label conditioning. So how we did this was we converted class labels also into tensors and concatenated them with a 3-channel image tensors. And so because of this, our generator was able to generate images with respect to a particular defect class. So conditional Wasserstein GAN with gradient penalty use Wasserstein loss function which helped in stable training. And we also had gradient penalty to enforce Lipschitz constraint. The critic, which is basically the discriminator in this case, was updated 5 times per generator update. For a weighted ensemble, so each GAN architecture was assigned a weight based on its FID score. Lower FID score meant higher weight and more contribution to our ensemble model. The weights were normalized to obtain a sampling probability, and synthetic images are generated using probabilistic sampling. For our evaluation methods, we first start off by visual inspection to get an intuitive idea about the performance of the model, followed by FID, which essentially measures the similarity in distribution between our original data set and the synthetic data. We then perform a TSTR, which is basically train on synthetic and test on real, which is the industry standard. This helps us validate the real world usefulness of our models. Coming to the individual performance of each GAN model, DC GAN failed due to model collapsing and unstable training. As we can see, the outputs is pretty noisy and unclear. The FID scores were 67 and the TSTR scores were 0.18. For conditional GAN, adding conditionality didn't really improve the performance much. The TSTR and FID were 0.037 and 28 respectively, which is not a significant improvement, and the output, as we can see, is still noisy and unstable. So CWGAN GP was a breakthrough model using Wasserstein loss and gradient penalty, provided highly stable training. As we can see, the images generated are quite realistic, and the FID scores are 1.17 and the TSTR was 0.2070, which is a significant improvement from the previous two. And coming to the ensemble paradox, our dataset was heavily weighted. So since CWGAN GP had the best FID scores, it contributed 94.41% to our ensemble model, and the remaining was from the other 2 models. But despite this, even we found that even minimal amounts of low fidelity data from CGAN and DCGAN led to dilution of the performance of the overall ensemble model. That's why the TSTR scores were dropped to 0.081. So in conclusion, DC GAN didn't really perform really well. It had highly unstable training. Conditional GAN, adding conditionality didn't fix the issue of stability. CWGAN GP, we were able to train it pretty well with extremely stably, and it was able to generate realistic synthetic data. And in our ensemble model, the quality was diluted by the weaker models. So our key takeaways are that PCB defect augmentation requires sophisticated generative architectures like CWGAN, which demonstrated unparalleled performance to stable training. And we also found that in generative augmentation, composition integrity heavily outweighs new dataset volumes. So even a small amount of minimal amount of low fidelity data from our weaker models significantly affected the overall performance of the ensemble model, and it diluted the quality. Our future research will focus in two main areas. Uh, Firstly, improving the generative fidelity using a diffusion GAN hybrid architecture and creating strict rules for checking synthetic data, since there is no current industrial standard for this. Thank you.
Thank you for your presentation. We will now open the floor for questions. I have a question.
Yes, sir.
My question is, how do you ensure that GAN-generated PCB defects improve detection performance without introducing bias or overfitting?
Yes, sir. So in traditional augmentation, what we do is we just rotate the current data or flip it or just essentially increase its size. So it's not really creating any new defect patterns. It's just same data over and over again. So, but with GAN architectures, we are learning the underlying features and features of our data, and it's able to create new defect patterns and new data set.
Yes. Thank you once again for your contribution.
Thank you.
Our next presentation will be by Zdravka Simonov, who will be presenting Regional Workforce Distribution and its Economic Impact, a comprehensive GIS-based study from data acquisition to findings visualization. Zdravka, you may now present your paper.
Hi, everybody. Now I'm going to put my presentation. So can you see it? Is everything working fine? Guys?
Yes, everything is visible. You can continue.
Okay, thank you. So good day, colleagues. Thank you very much for giving me the chance to be a part of your conference. My name is Zdravka Simonov, and I'm an assistant professor, doctor at the Technical University of Sofia at the Department of Computer Systems, the Faculty of Computer System and Technology. Thank you once again for the opportunity to present my research. The title of my study is Regional Workforce Distribution and its Economic Impact, a conference GIS-based study from data acquisition to findings visualization. The research examined how the spatial distribution of the workforce influence regional economic development. Geographic information systems are used as the main analytical tool. GIS makes it possible to combine economic indicators with geographic space. The study follows a complete GIS workflow. It starts with data acquisition, continues with integration and spatial analysis, and ends with visualization and interpretation of the results. So workforce distribution plays a fundamental role in regional economic development. where people work affects employment, income levels, and industrial activity as well. Economic indicators are spatially dependent. This means that jobs, wages, and industries are linked to specific locations. Traditional economic analysis mainly relies on statistical tables. While useful, these tables often hide spatial inequalities. GIS enables spatially informed economic analysis by linking indicators to geographic locations. GIS reveals regional imbalances and also hidden patterns. The first objective is to analyze the spatial distribution of the workforce. This includes identifying where employment and unemployment are concentrated. The second objective is to access regional economic performance. Key indicators such as employment, income levels, and industrial structure are examined. The third objective is to apply GIS-based spatial analysis. GIS is used not only for visualization, but also as an analytical environment for integrating socioeconomic data. The study is conducted in the national context of Bulgaria. Two municipalities were selected, Varna and Burgas. They are economically significant and share similar industrial characteristics. Despite these similarities, they demonstrate different economic outcomes. This makes them suitable for comparative analysis. The reference year is 2024, which reflects the most recent labor market conditions. All datasets used in this research come from official and reliable sources. For example, population, employment, unemployment, and salary data were collected from the National Statistical Institute of Bulgaria and the National Open Data Portal. European level labor and spatial datasets were obtained from Eurostat, ensuring comparability. Industrial and regional economic data were collected from regional profiles and mapping of the Bulgarian economy, which provide detailed information about companies and industries. ArcGIS Pro was used for data integration, spatial analysis, and map creation. ArcGIS Online was used to publish the web map and improve its design and usability. ArcGIS Instant Applications was used to create an interactive web application. This allows users to explore the data dynamically rather than viewing static maps. The data integration process involved several steps. First, all datasets were cleaned and converted into compatible formats such as CSV and shapefiles. Second, demographic and employment data were linked to municipal boundaries using attribute joins. Third, industrial data was connected to geographic locations using spatial joins. This process allowed all indicators to be analyzed within a unified spatial framework. Figure 1 presents the industry dataset integrated into ArcGIS Pro. It includes company level information such as revenue, number of employees, and location. The dataset supports the analysis of industrial specialization and concentration. It also helps explain how industry structure influences workforce distribution. Figure 2 shows population and labor indicators at the municipal level. These include population size, employed and unemployed people, and average salary. This information forms the basis for analyzing workforce distribution and labor market disparities. Linking these indicators to space reveals spatial labor market patterns. First, I created the main web map in ArcGIS Pro. After that, I improved the design and usability in ArcGIS Online. As you see, large symbols show industries that appear more often in a municipality. Small symbols show industries that are less common. This makes the map easier to read. Users can quickly see which industries are dominant and which are not. After finishing the design in ArcGIS Online, I exported the map to ArcGIS Instant Applications. This step turned the map into an interactive web application. So users can explore the data online, not just look at a static map. The bottom image shows the two stacked charts. The first chart is average gross salary by city. The second chart is employed and unemployed population age 15-64 by city. These charts complement the spatial maps. The salary chart allows comparison of income levels across cities. And the employment chart highlights differences in labor market performance. Okay. In this section, I analyze workforce distribution, industry population, and economic indicators. The goal is to understand how these factors interact and how they affect the regional economy. Analysis helps economic planning. It also helps identify problems and possible solutions. I extracted data from the web map application. So the results show clear differences between Varna and Burgas. Varna has a larger population and higher average salaries. Burgas shows stronger industrial concentration with higher company revenue and workforce size. These differences reflect distinct economic structures. The image on the slide corresponds to figure 6 from the article, Comparative Analysis of Workforce Distribution Results. I interacted with the web map application, selected Varna and Burgas, and extracted the key indicators displayed in the map and charts. I then summarized the values in Microsoft Excel. So the results...
1 minute remaining.
Oh, okay. The results show that Varna and Burgas have different strengths. Varna has a large and better paid workforce. Burgas has a powerful industrial base, especially in maritime activities. Now the study confirms. Now I will conclude the study. This research shows why GIS is very important for studying workforce distribution and regional economies. By combining population data, employment data, and industry data, GIS help us see clear spatial patterns. These patterns support better decisions based on real evidence. The study helps us understand how population is distributed, how the labor market performs, and how industries are structured in different regions. Finally, this study can be extended in the future. Future research can include more municipalities. It can also cover national or European level analysis. This would help us better understand workforce distribution. It would also show how it affects regional competitiveness and economic resilience over time.
Thank you for your presentation.
Yeah.
Thank you.
Okay. Thank you
We will
very
now
much.
open the floor for questions.
I have a question. So I want to know the method that you used and the analysis technique that you used. Is it only applicable, or is it only going to be used specifically for the two regions that you used it in, or can it be used worldwide?
Would you please repeat the question?
Yes. So my question is, the data that you got from the two regions that you chose, the technique that you used for your study, can it be used worldwide with other regions, or was it specifically designed for the two regions you chose?
Oh, thank you. Yeah, yes. The method can be applied worldwide. The GIS workflow used in this study is not limited to Bulgaria. It is based on standard spatial data, workforce statistics, and widely used GIS tools. As long as a reliable labor market and geographic data are available, the same approach can be applied to other countries or regions. This makes the method flexible and suitable for international and comparative studies.
Okay, thank you very much.
Yeah, thank you very much.
Okay, thank you once again for your contribution.
Thank you. Thank you so much.
All right, we'll be moving on to the next presentation now. We have Georgia Reiki Sharon, who will be presenting the innovation of medical diagnostic technology, a case study on stroke diagnosis. You may now begin.
Thank you very much. Can you see my screen?
Yeah.
Awesome. Good afternoon, ladies and gentlemen. Oh, excuse me. I just want to. Awesome. Good afternoon, ladies and gentlemen. My name is Georgia Shannon, and today I have the privilege of discussing the critical yet overlooked engine of the healthcare system, the innovation of medical diagnostic technology, and the barriers faced during the process. Ladies and gentlemen, imagine this: a young European businessman in his late 20s, filled with ambition, drive, and convinced he can build a multi-million-dollar company around a breakthrough medical diagnostic technology. Not for prestige, not for headlines, but for the undiagnosed patients worldwide, in Africa, Malaysia, Asia, or Australia. Patients misdiagnosed, mistreated, or simply forgotten. Ill children are waiting for the day when someone or something can give an answer to their circumstances. This businessman navigates regulatory hurdles, escalating validation costs, cautious investors, and complex procurement systems. With each burst of funding, new hope arises. And with each delay, the gap between innovation and impact widens. The science is ready, the technology more advanced than ever, and he knows the tests are accurate. Its challenge is not innovation, it's implementation. If only the two worlds could meet. Fast forward 30 years. The businessman has sacrificed time with his family, finances, and emotional resilience pursuing the innovation. The diagnostic test never fully reached the market, not because it lacks value, but because the barriers prove stronger than the breakthroughs. And the undiagnosed patients are waiting, lower quality of life, bravely enduring suffering, or potentially dead. Eventually, the businessman Once an ambitious 20-year-old, now late 50s, is faced with reality. He needs to face bankruptcy. The story is not about scientific failure. It's about systematic barriers and valleys of death. The space between technological capability and real-world implementation and adoption. Ladies and gentlemen, the question we are faced with: how many promising technology innovations are lost in the gap between technological adequacy and market adoption due to system barriers? Medical diagnostic technologies form the very foundation of modern medicine. Estimates suggest that up to 70% of clinical decisions